So this is a far less than comprehensive study of pumps. There is a pumps class, but I'm going to kind of generally explain how a centrifugal pump works, the most common types of pumps. When I say most common, that's more dependent on scale, but for large volumes of water, not that these three pumps can only do large volumes of water, and a submersible pump actually is generally not a large capacity pump. But the principles apply to, essentially regardless of scale. But in agriculture, these are our most common pumps. Okay. So the centrifugal pump, turbine, and a submersible pump. What's misleading is that they all work with a centrifugal action, essentially. Why just the centrifugal pump is called a centrifugal pump, or excuse me, why one pump is named the centrifugal pump when they're all working with that same kind of mechanism, I don't know. But to sort of, I guess, break them down a little bit, what we're seeing right here is a centrifugal pump, just like that cutout that I have right there. Centrifugal pumps are most often going to be like this, having a motor, the driving unit, attached to the pumping unit. So this whole thing isn't the pump. This section right here, this is a single stage impeller, just one stage for the water intake. The pressure is created there, and let's see, where's this thing? It's assume that, yeah. So this is our outlet here. The turbine pump, that picture there is just the motor. So the driving unit, which is attached to a drive shaft, kind of like this one, and then spinning the impellers down there in the bottom, or in the water itself. Yes, we haven't really talked about it much at this point, but when we were looking at the suction head on the suction side of our pump with this total dynamic and static head evaluation, we were seeing that, obviously we can have pressure supplied to the pump by having the pump located at a place lower than the water level. So if we had our water supply coming from an overhead capacity or cistern storage capacity of some sort, and that's a big advantage because that was pressure that we didn't need to create, or to maybe it saves us from purchasing a pump with more horsepower. Because that would be water that is being supplied to the pump at a pressure dictated by the elevation, and so pressure we don't have to create ourselves or by the pump. And that's why it is really a significant advantage to have your pumping unit, like the turbine pump, with its bowls in the water. So that is water that is constantly applying a pressure to the inlet versus a scenario where we'd have to try to lift that water up to the pump and then expended pressure. Okay. And the submersible pump, like the name suggests, that, like this one here, here's the, I don't know if this, I assume this whole thing, this might be a two-stage red jacket, two-stage pump. Behind that, the projector there is another example of a submersible pump, but a pump that is both the driving unit, the motor, which is electric, and the bowls of the pump are lowered down into the casing or into the well. All right. So again, they all work with centrifugal force. I think we're all fairly aware of what centrifugal force is, but basically the force that's created with a circular movement. Just and the further out from the center, the greater the centrifugal force. So the larger the diameter of the bowl assembly, that intake unit, or this is the bowl right here. The larger that thing is, the greater capacity we have for with that pump. Okay. Of course, larger bowls will generally require larger horsepower, more power to drive the things. Okay, but fluid enters the pump. The water is going to enter the pump through the eye of the impeller, which is just the center point. Oftentimes I use impeller and bowls interchangeably. That's pretty common. So this is the impeller. This is the eye of the impeller where the fluid enters. Okay. Of course, that bowl is rotating. Water is going to be, the centrifugal force moves the water outward, and the little casing area on the external or on the outside of the bowl or the impeller, this kind of furthest exterior area is called the volute. So the water, the pressurized water is sent to the volute, and that centrifugal force moves the water out. Simultaneously, we're creating areas of lesser pressure where our velocities are the highest, which is actually just on the sort of the back side of the impeller fin. I was talking about, velocity and pressure relationships. So we have this area of extremely high pressure being created on the outside, relatively less pressure, and so we've got, what it ends up doing is it's actually creating a vacuum by that high velocity movement of water that is going from high velocity water to high pressure water when it hits that volute, the external side of the, I don't really need to go into it a whole lot further than that, but with that inverse relationship between velocity and water, where the velocity is the highest, we have pressures of the least amount, which ends up creating an area of lesser pressure and literally sucking, I guess you could say, or pulling, or actually allowing water to just naturally move into the pump and continue to move into the pump to displace the water that's going out. Okay. Let's watch, actually, I've only watched the first couple minutes of this video here, but we might just stop after a couple minutes. Gives us a pretty fair visual.
Plants use many types of pumps to move process liquid. One of the most common types of pumps in use today is a centrifugal pump. A centrifugal pump uses one or more impellers to create a centrifugal force that pushes the process liquid through the pump. While there are a number of different types of centrifugal pumps, they can be grouped into two basic categories: single-stage pumps and multi-stage pumps.
A single impeller or multiple impellers?
Centrifugal force to move liquids. Centrifugal force is the force that exists when an object or material moves in a circular motion. This force causes the object or material to move outward, away from the center of rotation. In a centrifugal pump, what moves outward is the process liquid. We can see how a centrifugal pump works by using this simplified illustration. All centrifugal pumps have an inlet, a casing, and an outlet. Inside the pump's casing is an impeller. It has a series of curved vanes that extend out from its center. The pump's casing is designed so that the area around the impeller creates a gradually widening spiral channel. This widening channel is known as the volute. Since this pump has only one impeller and one volute, it is referred to as a single-stage pump. During operation, a driver
Motor
rotates the impeller, creating a centrifugal force that throws the process liquid outward into the volute. The outward movement of the liquid causes two things to happen. First, it creates a reduced pressure area at the suction eye of the impeller. This area of lower pressure draws more liquid into the pump and provides a constant flow of liquid. Second, it causes the liquid to gain speed. This happens because as the liquid is forced to the outside of the rotating impeller, it must move faster to keep up with the impeller. As the liquid flows away from the impeller, it spreads out to fill the volute. The expansion in the volute causes the liquid to slow down. The expansion in the volute causes the liquid to slow down and its pressure to increase. The increased pressure moves the liquid through the
essentially a transition from high velocity to high pressure.
One way that centrifugal pumps can be categorized is by the way liquid flows through. Three common flow path classifications are radial flow, axial flow, and mixed flow. In centrifugal pumps that have a radial flow design,
This isn't stuff you guys need to remember for this course. I'm just think this guy does a good job.
Or radially from the suction eye to the tips of the vanes. A radial flow pump takes advantage of the maximum amount of centrifugal force that the impeller develops. Generally, radial flow pumps are capable of higher discharge pressures, but they don't move as much liquid as other types of centrifugal pumps. In centrifugal pumps that have an axial flow design, the impeller moves the liquid through the pump along a path that's parallel to the pump shaft. In this type of pump, the liquid is moved mainly by the propeller action of the impeller's vanes. This impeller uses only a small amount of centrifugal force to move the liquid. As a result, the discharge pressure of an axial flow pump tends to be lower than that of a radial flow pump. However, an axial flow pump may be able to move large quantities of liquid. Mixed flow pumps combine the characteristics of radial flow pumps and axial flow pumps. They use centrifugal force and the propeller action of the impeller's vanes to move the process liquid. For that reason, a mixed flow pump can develop a relatively high discharge pressure and still move a large quantity of liquid. In some instances, it's often necessary to keep a pump driver above the liquid while the pump is submerged in the liquid. One type of centrifugal pump that you may find in these applications is a vertically mounted centrifugal pump. We would use this
Or a turbine pump.
of a vertically mounted centrifugal pump and its driver to see how this type of pump works. The pump itself is submerged in a tank containing the liquid being pumped. The driver, which is an electric motor, is mounted above the pump on top of the tank. Its shaft is connected to the pump shaft by a coupling. This pump shaft is much longer than those found on most other centrifugal pumps. On any pump with a long shaft, it's important to keep the shaft in its correct position so that the pump will operate properly. So several bearings are used to keep the shaft properly aligned. Now on this pump, there is no suction pipe. Instead, the suction of the pump is submerged in the liquid being pumped. The suction is covered by a strainer, which prevents trash or debris from clogging the pump and causing excessive wear. The pump's impeller is also submerged in the liquid. This helps to ensure that the pump is always primed. This means that the casing is filled with the process liquid.
You guys want to keep watching this? I mean, it's
During operation,
taking it further
the liquid is
than...
drawn in through the suction
Cool, okay.
And then pumped through the discharge piping, which extends up and out of the tank. All centrifugal pumps work by creating a centrifugal force. This force moves the liquid through the pump and increases the liquid's pressure. In applications where large increases in pressure are needed, multi-stage centrifugal pumps are often used. A multi-stage centrifugal pump contains two or more impellers and volutes in a single casing. Here's a simplified cross-section of a three-stage centrifugal pump. Each stage of the pump has its own impeller and volute. In the volute, the liquid's pressure increases. Each of the first two volutes discharges into the suction eye of the stage that follows it. The third stage volute discharges into the pump's outlet. So in this pump, the liquid flow path is from one end to the other. This is a five-stage pump. It has 5 impellers and 5 volutes. The first 3 stages are located here, and the 4th and 5th stages are located here. But, as you can see, the liquid's flow path is different from that of the 3-stage pump we just saw. In this pump, liquid enters through the suction and flows into the impeller of the first stage. This impeller has a suction eye on both sides and is often called a double suction impeller. From the discharge of the first stage volute, the liquid flows into the second stage suction eye. Then out of the second stage discharge and on to the third stage suction eye. And out of the third stage discharge to the suction eye of the fourth stage.
I wonder what the advantage of sending it back like that versus keeping it in line.
To the suction eye of the fifth and final stage. After the liquid passes through the fifth stage, it leaves the pump through the discharge piping. Regardless of how the impellers on a centrifugal pump are arranged, or how many stages a pump has. The liquid's pressure increases as it passes through each stage. This creates a thrust across the impellers in each stage. This thrust, known as axial thrust, is caused by the difference in pressure between the suction eye and the balloon. Pressure across the impellers, axial thrust is created, and it tries to push the pump shaft toward the suction eye. In order for the pump to operate properly, the thrust must be offset. On some pumps, the thrust is offset by using a thrust bearing or a device known as a balance piston or balance drum. On other pumps, the thrust is offset by the arrangement of the impellers. This pump has a balance piston. During operation, some of the fluid leaving the pump flows along the shaft and exerts pressure against the balance piston. That pressure tends to force the pump shaft away from the suction eyes and reduces the total thrust. Any fluid that passes by the balance piston is returned to the suction side of the first stage. Now on this pump, the arrangement of the impellers is used to offset axial thrust.
Okay. I think this is interesting, but we really don't need to
So the pressures on both
use
sides
class
of the
anymore.
impeller are
Okay. Okay, I think we covered that. But again, remember, the higher the velocity of the impeller, the greater the energy transfer becomes into pressure. Okay? Yes, sir?
Just real quick, if you have a pump in the field with a power source, how does the power get there?
Kind of dependent on the scenario, but I mean, a lot of times, I mean, there's no real reason for the pump to be in the middle. You know, I mean, I wouldn't place a pump that wasn't near a power source unless I was working with